Now that we've taken a look at methane, we're going to examine ethane, which is adding one more carbon and creating a chain now. And so we're going to examine ethane and talk a little bit about ethyl compounds, and we're going to learn a new type of drawing called a Newman projection. So if you envision a methyl compound, if the X, the substituent, is another methyl group, then you get methyl-methyl, or we simply call this ethane. And so if we take a look at the three-dimensional structure of ethane, we simply have two methyl groups that are connected together. Each methyl group has is tetrahedral in geometry, right? And of course, the bond angles are close to 109.5 degrees. As a matter of fact, each methyl group basically stretches that bond a little bit, and so what happens is the hydrogen-carbon-hydrogen bond shrinks because the carbon-carbon-hydrogen bond is lengthened a little bit, and this is simply due to electronic steric strain. Now, the cool thing about ethane is if you look at that carbon-carbon bond, it's a sigma bond. So sigma bonds are cylindrical in nature, which means that any cylindrical molecular orbital has free rotation. We can think about the substituents, the other substituents attached to that being able to rotate freely about. Now, how free is that? We're going to take a look at, and we're going to realize that it's not exactly free rotation. Because what happens is you get two main conformations. So conformation is simply another way of looking at a molecule in three dimensions through a rotation. Now, what do I mean by that? So let's take a look at how I drew ethane in that previous slide. And we see that what happens if I rotate 60 degrees about that carbon-carbon bond. What happens is the hydrogen that is that dash is now going to come into the plane of the board. The hydrogen that's the wedge is actually going to rotate down. It's still going to be a wedge. And the hydrogen that's currently in the plane of the board, if we're envisioning the right side rotating. So basically I'm going to keep the left carbon stationary and the right side I'm rotating. So that the hydrogen in the plane of the board is actually going to go behind me. The result is, notice the carbon on the left doesn't change, but now the carbon on the right has a new orientation. And if we examine this structure, basically, so there's my little eyeball, and I'm examining this structure down the carbon-carbon bond. What I see is that the hydrogens, as a matter of fact, all of the hydrogens are going to be overlapping one another in essence, right? So the hydrogen on the carbon behind me, which would be to the left, is going to be behind the hydrogen on the carbon to the right. We call this eclipsed, so the hydrogens eclipse one another. So what we have are, these are the two conformations. The one on the right we call the eclipsed conformation because all of the hydrogens are eclipsed, are eclipsing one another. And the conformation on the left is called staggered because all of the hydrogens are staggered from one another. Now, the angle between the hydrogens is called what we call the dihedral angle, and we label that theta. So theta is an angle between the hydrogen in front and the hydrogen in back. And when we have a staggered conformation, theta is 60 degrees. And so what that means is the hydrogen in front is 60 degrees from the hydrogen in back. And when we have an eclipse conformation, then theta is 0 degrees, right? Because they are eclipsing one another. Now, sometimes looking at these three-dimensional dash wedge construction, it's kind of hard to see those angles. And because of that, we have a new way of essentially drawing the structure, and it's called a Newman projection. So the Newman projection sights down a particular carbon-carbon sigma bond, right? So in the previous slide, we saw that we're looking down a carbon-carbon sigma bond. Now, how do you draw Newman projections? At first, they might be a little intimidating, but once you get the hang of it, they're actually pretty easy, and you can really see the dihedral angle much better in a Newman projection. So the first thing you want to do is you're going to place a dot for the carbon that you're looking at that's in front, right? So here's my dot. And then you're going to draw the 3 carbon-hydrogen bonds that are coming off of that carbon. So we're not going to draw the carbon-carbon bond, we're simply going to draw the carbon-hydrogen bonds, because if we're looking down that carbon-carbon bond, we actually can't see the bond, but we can see the other 3 bonds to the hydrogens. And it happens that when you're looking down that bond, the angles actually look like they're 120 degrees. This is a great opportunity for you to get your model kit out and actually construct a molecule of ethane and actually see how looking down a carbon-carbon bond that looks like. And what you're going to see is that you have this construction that looks like in essence almost a trigonal planar geometry. It's not trigonal planar, don't get me wrong, but that's kind of what it looks like if you're sighting down that carbon-carbon bond. So we have the hydrogens that are attached to that front carbon. Now, to represent the back carbon, what we're going to do is we're going to draw a circle around that dot, basically, and it's going to look like this. And so now we want to draw, the last step is drawing the 3 carbon-hydrogen bonds connected to the carbon in the back. And of course we can do this in one of 2 ways. So here I have the carbons that are basically 60 degrees from one another, right? This is what the staggered conformation looks like. So that bond angle, that is the dihedral bond angle. It's that hydrogen, carbon, carbon, hydrogen bond angle, and it's 60 degrees. This is the conformation of the staggered conformation. Now, I can draw it another way too, right? So I can draw that front carbon that I'm not going to rotate, and so all of the hydrogens are in the same position, but now in an eclipsed I'm going to rotate 60 degrees. Now how do I represent that? Well, it becomes a little bit of a challenge because ideally the hydrogens you can't see, but in order to represent that we have to be able to visualize the hydrogens and know that they are behind these front hydrogens. So what we do is we get as close as possible to the front hydrogens, right? And so it looks something like this. And this is how we represent the eclipsed conformation, recognizing that the hydrogen-hydrogen dihedral angle is 0 degrees. So it's 0 degrees, right? This is theta. And in reality, those hydrogens, if we're looking perfectly down that carbon-carbon bond, I would not be able to see the hydrogens in the back, right? Okay, so when theta is 0 degrees, there's actually potential overlap of the carbon-hydrogen sigma bonds. We certainly don't have any steric strain. There's enough space for the atoms to fit fairly nicely. But what happens is when you have an eclipsed conformation, right, when theta is 0, the carbon-hydrogen sigma bonds actually overlap. And the reason for this is because the symmetry is right. They're in the same plane as one another. Now, let's look at what happens in that molecular depiction. So here we have an eclipse conformation, right? So I'm basically showing the hydrogens that are going back and coming out at us, and I'm going to emphasize the carbon-hydrogen bonds that are in the plane. So if I represent that carbon, that sp3 orbital of carbon, that's in the plane of the board, and the other carbon also has an sp3 hybridized orbital. And of course, we know that they're going to overlap with the 1s orbitals of hydrogens, and they form a bond, and we call these the sigma bonds, right? These are the sigma bonds. And these are the bonds that we are going to be looking at. Since they're in the same plane as one another, then there is an interaction between the two of them. Now, what does that interaction look like? So we start with, drawing a molecular orbital diagram. We start with a carbon-hydrogen sigma bond on the left and a carbon-hydrogen sigma bond on the right. They're going to mix. And how do they mix? They can mix in one of two ways. I can either add the two sigma bonds or I can subtract the two sigma bonds. Now, notice what happens to the energy. There is an energy difference, right? The sigma plus sigma doesn't have as much of a stabilization effect as the sigma minus sigma, right? So I'm creating these new bonding and antibonding orbitals, right, between the two carbon-hydrogen sigma bonds. And because when I add the two together, there isn't a huge amount of stabilization going on. And when I think about how many electrons I have, I know there are 2 electrons in one sigma bond. There are also 2 electrons in the other sigma bond. When I add those 4 electrons into my new molecular orbitals, I get a net effect that at first glance looks like there should be no bonding whatsoever. However, because of the energy change, because the energy that I get from creating a bonding orbital is actually less than the energy that I have to add into the antibonding orbital. And one of the main reasons for that is look at those green lobes there. They're in fairly close proximity to one another, and so there's a repulsion that occurs. And the net effect is that that energy, the destabilization energy, is greater than the stabilization energy. And so we have a net destabilization when you have 2 bonds that are eclipsed with one another. And we often call this the dihedral strain. The dihedral strain. So it's not a steric strain in the sense of 2 atoms with electron density interacting, but it is a dihedral strain from a small net overlap of the sigma bonds between carbon and hydrogen and the other carbon and hydrogen, right? So that's important to be able to distinguish the difference between the two. And you'll see this strain being called, a few things. A dihedral strain is one. Angle strain sometimes you hear, although I think that's misused. Eclipsed strain is a good one. So dihedral strain or eclipsed strain you'll often hear. All right, so now let's see what happens when theta, the dihedral angle, is 60 degrees. So now we have a staggered conformation. Well, when that occurs, there's an actual overlap of one of the carbon-hydrogen sigma orbitals with the sigma star orbital, the antibonding orbital of the other carbon-hydrogen bond. Let's take a look. So here I'm drawing the carbon-hydrogen bonds that are that are not in the plane of the board. I'm going to focus on the carbon-hydrogen bonds that are in the plane of the board. So the carbon on the left is going to have a carbon-hydrogen bond that's pointing up, and we can represent that sp3 orbital overlapping with the 1s orbital of hydrogen, and we have that sigma bond. Now, of course, the carbon on the right also has a sigma bond with hydrogen, but it also entails a sigma star bond. And the shape of the sigma star bond looks like this. Notice the in-phaseness of that sigma star with the sigma bond of the carbon-hydrogen bond on the left. So here I have hydrogen, and that is a sigma star bond. Notice the out-of-phase orientation of the 1s orbital of hydrogen with the sp3 orbital of carbon. So that is a sigma star bond. But the cool thing is that there is overlap between the sigma bond, carbon-hydrogen bond and the sigma star carbon-hydrogen bond of the other carbon. Again, if we construct a molecular orbital diagram, we know that sigma bonds are actually lower in energy than sigma star bonds. But if they mix, what happens is we get a molecular bonding orbital, which is sigma plus sigma star, and an antibonding orbital, which would be sigma minus sigma star. Now, this is the key. The sigma bond has electrons in it, right? There are two pair of electrons. The sigma star bond is empty, and so there are no bonds in that. What happens is then when those two mix, my bonding orbital gets the new electrons, the two new electrons, and my antibonding orbital has no electrons. Therefore, there is a net stabilization from the staggered, remember these are staggered, bonds. So in essence, the sigma bond of a carbon-hydrogen can actually interact with the sigma star of the other carbon-hydrogen when it's in that orientation. Now, we can actually plot theta, right, the dihedral angle, as a function of potential energy, because we see that eclipse conformations are higher in energy, they're destabilized, and staggered conformations are stabilized. We call this plot a potential energy diagram. And the way it looks is if we essentially plot energy versus a reaction coordinate, right, we get this oscillation effect. So if we start at 0, where if we have an eclipsed conformation, now what happens? As we rotate about that bond, it becomes more stable. And so we rotate to 60 degrees, now we have a staggered conformation. Now, as we then continue to rotate about that bond, what happens is, once we get to 120 degrees, now we have another eclipse conformation. And then we can rotate another 60 to 180, and now we have a staggered conformation. And then we can rotate another 60 to 240, and we have an eclipse conformation, higher in energy. And then back down to 300, we have another staggered, and then a full 360 rotation gives us back to the eclipsed conformation. So every maximum is eclipsed, every minimum is a staggered conformation. So eclipsed to staggered to eclipsed to staggered and back to eclipsed. And we call the eclipsed conformation, so there's a maximum energy there, right? And the energy difference between the eclipsed and the staggered conformation for ethane is 2.9 kilocalories per mole. Now we're going to see other conformations have a little slight variation in that energy, but in essence around 3 kilocalories per mole to go from a staggered to an eclipsed conformation. So if you think about that, if you think about this, every time we go to an eclipsed conformation, there are 3 eclipsed bonds. In essence, what we have is an energy of 1 kilocalorie per mole per eclipsed bond. And that's something to think about. So every dihedral angle strain amounts to approximately 1 kilocalorie per mole in energy, right? So we add the 3 up and we get 3 kilocalories per mole. And that maximum energy is what we refer to as a transition state. So in any potential energy diagram, the maximum energy is always referred to as a transition state, right? It's the transition from a higher energy structure into a lower energy structure. Now, let's think about ethyl compounds, right? Ethyl compounds are similar to methyl compounds in that what we're going to do is, we saw with methyl compounds, we simply take the methyl group and we add some functional group, right? So now we're going to take an ethyl group. We're going to remove a hydrogen, and so instead of CH3CH3, we have CH3CH2. That's an ethyl group, and we're going to add a functional group. So here is an example. We have CH3CH2, right? We've removed a hydrogen, and now we've replaced it with the functional group OH, which is an alcohol. And so now we get an alcohol that has 2 carbons in its chain, right? And that's called ethanol. Sometimes this is referred to as ethyl alcohol. Another example is ethyl bromide, right? Ethyl bromide, and of course, all of the halogens have their own name: ethyl chloride, ethyl iodide, ethyl fluoride, right? Now, one of the things that is different with ethyl groups versus methyl groups, you might start thinking about the substitution, how the substituent is actually on that carbon chain. So when we look at the Lewis structure looks like this. Now, I've placed the bromine on the carbon, at the end, at the right end of the structure. But notice I could place the bromine at any of the, essentially replacing any of the 6 hydrogens. So what if I, instead of replacing the bromine at the end, replace the bromine on the top right? Are these two structures any different? In fact, they're not, right? Remember, we have to think about these structures three-dimensionally. So oftentimes students can get confused about saying, oh, okay, these two are different structures simply because of the placement of the bromine. In reality, that three-dimensionality, there's free rotation, and therefore when I place a bromine on, at the end versus when I place the bromine at the top right, it doesn't really matter. And as a matter of fact, I can place the bromine on the other carbon, and it also doesn't matter, right? Because I can essentially rotate that molecule around to give any of the other 2 structures, right? So one of the things that we need to be aware of is thinking about what carbons and what hydrogens are different and what are equivalent with one another. And so we say that all 6 hydrogens of ethane are equivalent to one another, and therefore it doesn't matter where I put the bromine, all 3 of these structures are equal to one another. And that becomes important, especially later on when we add another carbon, add more carbons. We're going to see that not all carbons are equivalent, not all hydrogens are equivalent.